All right, team, welcome back. We're going to talk a little bit about polarizers and look at some of the equations involved in polarization. Really neat. Hopefully you've seen the videos I posted before here, and Guy showed you on an overhead projector sort of how polarizers work. There's some videos after this where a LCD monitor is torn apart, and they actually look at how polarizers work and are used for LCD monitors. It's really neat things, I think. So let's take a look a little bit about polarizers. First, we need to, polarizers only work with transverse waves. Now, if you recall, a transverse wave, the wave is moving to the right. So that means the energy is moving to the right. But a transverse wave is one that the oscillation of the particles is perpendicular to the direction of motion. So while the while the wave may be moving to the right, each individual part of the medium is only oscillating in one direction, up and down. Now, we typically draw transverse waves a little bit like this. We notice that while these particles are oscillating up and down, the waves move to the right. But this gives us not a very good illustration of what transverse waves actually are. So for example, let's say I had a transverse wave coming out of the screen right at this green dot. My question to you, and I want you to pause and think about this, is what is the direction that the light coming just from any normal source you see, any dot you see around your house or whatever, how is the light as it's coming towards you out of your screen, how is it oscillating? How would it be oscillating? Okay, so many of you may have said, oh, it's oscillating up and down. And it definitely could be. Yes, that would be a perpendicular direction. If the direction of the wave is out of the screen, it could be oscillating up and down. It could be oscillating left and right. Certainly that could be the case. That's still perpendicular. It could be oscillating diagonally like this, like this. You can come up with any infinitely small angle, and the light could be oscillating in that direction. We call this, we call a wave, usually we talk about light with this, light that is oscillating in all directions. We call this unpolarized light. It's sort of disorderly. It's all over the place. When you look at the sunlight coming down from the sun is unpolarized. You have light that is oscillating in all 360 degrees of direction, and it is definitely not orderly. So what we do with polarizers, what a polarizer does is it filters this out. A polarizer will only let light through, or energy through, that is oscillating in the direction of the polarizer. Let me show you an image here. Like say the images can draw this much better than I can draw on my little screen here. So here's a polarizer. Let's look at the left side first. On the left side we have unpolarized light. Notice there are several different waves. All the waves have slightly different directions of polarization, planes of polarization we call this. In fact, there are 1, 2, 3, 4 different waves coming in to this polarizer. Now what the polarizer does is it acts a little bit like a lot of very, very, very skinny little bars. And what happens is when the polarized light hits this polarizer, anything traveling in that direction, anything traveling in the same direction as the little lines will get absorbed by the polarizer. The energy will hit the polarizer, it'll actually make the little particles, these lines, move back and forth a little bit, and it will absorb the energy. This polarizer only lets waves with one plane of polarization through. So while you have unpolarized light over here on the left side, on the right side, our light is now polarized. The light only oscillates in one direction. In this case, it's oscillating up and down while the wave is moving roughly to the right. Okay? This is what polarized does. Now, let me ask you a question. I'm going to have you think about this. what do you think happens to the power, let's just say the intensity of this light? How much energy per second per area is going to happen? Are we going to have the same energy? Let's say this is intensity I. Unpolarized light is intensity I. What would you guess the intensity of unpolarized light would be? Give you a moment to think about that. Hit pause. Okay, hopefully you thought that, well, it does look like we're losing some energy here. It looks like we're losing some. Now, some of you might have said, well, we're going to lose 1/4 because we had 4 different waves coming in, only 1 goes out. That's not the case, because what happens is, even though some of these diagonal lines, maybe they're not exactly the up and down direction, there is an up and down component to them. And so that energy will still go through. When we go from unpolarized light to polarized light, the intensity drops by half. Okay? The intensity always drops by half, no matter what. I could take my polarizer right here, I could rotate the polarizer to any angle I wanted, and while the plane of polarization would change, certainly, the intensity would still stay the same. It would still be I/2. Okay? So we're going from unpolarized light to polarized light. So this is the basics of polarization. Polarized light makes the light choose a direction. It only lets light oscillating in one direction through. Now, this is nice, but what about this? Let's say we have unpolarized light over here. Unpolarized, UP, unpolarized light. The unpolarized light is coming in, and we're going to make a polarizer that is sending vertically right here. And then we're going to put a second polarizer up. The second polarizer is going to be totally horizontally. And then we're going to see what the intensity is in different places. We start with intensity I. First question is, what is the intensity? So say position A, position B, position C. At position A, the intensity is I. What would the intensity be at position B? Well, hopefully you said any unpolarized light going to a polarizer of any sort, the intensity is going to be I/2. So now we have intensity I/2. The wave coming through the polarizer B is oscillating in and out of the screen. Something I wish I could show you in class. I'd be able to show you this a little easier. It's sort of tough to do on my iPad. But what intensity will we have through C? See, C is going to absorb anything moving horizontally, and it's only going to let the stuff that's oscillating vertically go through. And so the intensity at C is actually going to be 0. No light will get through. This is why we saw those videos earlier of the guy moving the polarizers around. When the two polarizers were at right angles to each other, when the angle between these two, in this case the angle between those two polarizers is a 90-degree angle. When that polarizer is at a 90-degree angle, you are not going to get any light through. It turns black. Now in the same situation, we could look at a similar type of thing. We're going to take unpolarized light. We're going to send it through, here's position D. We're going to have a vertical polarizer, and then we're going to have another vertical polarizer, E and F. So I want you to think through. If the intensity at D is I, what would the intensity at E be? And what would the intensity at F be? Give you a moment to think about that. All right, so at E, hopefully you said you're going to have I/2. Whenever unpolarized light goes through a polarizer, you're going to have half the intensity left. No diggity, no doubt. At F, well, only horizontally polarized light got through the first polarizer, and the second polarizer is only going to let through horizontally polarized, and that's the same light, so you're going to have the same intensity. That second polarizer will not affect anything because the angle between those two polarizers is 0 degrees. And so what we need is we need some kind of equation that's going to allow us to figure out, well, what is that relationship between the intensity and the angle? And we do have an equation. This is also found in topic 4.3. And we have an equation that says I, it's called Malice's law, by the way. I equals I naught cosine squared theta. Now, I don't like how mathematics writes down cosine squared. I always have to have a think, what do they really mean by that? What that cosine squared really means is simply this. You take the cosine of the angle, and then you square that value. That's what cosine squared theta. Because typically you won't put things in a calculator like the first image up here. Typically you put them in like the second image. So I want to make sure of that. Also know that when we're dealing with angles, you'll typically be dealing with degrees. We don't usually use radians for this because these are actual measurements, not mathematical constants. And so let's try this out. So let's tell me what things are. So see, so I is intensity after polarizer. I naught is intensity before polarizer. If you ever see a naught or a 0 as a subscript to something, that is typically going to mean that it's before. It's the intensity at time is 0, maybe. Theta is the angle between planes of polarization. Typically, what's going to happen is just like we did above, you'll have two polarizers. They'll be at a certain angle to each other. And so that's sort of how that's going to work. So let's try, let's look at this first example where we had 90 degrees. So the intensity before the polarizer, I naught, would actually be I over 2 because we're going to talk about this transition from B to C. So in this case, I equals I over 2. The cosine of theta, theta is 90 degrees. Now, if you know your stuff well, cosine of 90 is 0, and so the intensity is 0 watts per meter squared. Okay. Same thing on the right side. We're going to start with an intensity of I over 2. So intensity equals I over 2 cosine of 0 squared. If you know your trig functions, cosine of 0 is 1. 1 squared is 1. 1 times I over 2 is I over 2. So the intensity is I over 2. We can see this law definitely works pretty well. One trap they're going to maybe do for you on a test or a cognitive or worksheet or whatever is they will say the intensity of unpolarized light is I. And they may ask you for what is the intensity after the two polarizers. You need to realize that you're never going to put unpolarized light intensity into this equation. The light intensity you're putting into this equation will already be polarized. When you go through the first polarizer, you're going to drop by half automatically. Then you put that I naught in here and figure out your final intensity at position F. Okay? You'll see when we start getting into those problems and in cognitive how that works. But this is called Malice's law. So we can look at a slightly different kind of situation here. We could see, let's say, polarized lights of intensity I. Well, actually, let's put numbers to it. Of intensity 5 watts per meter squared. After second polarizer, intensity is 3 watts per meter squared. What is the angle between the two polarizers? Sorry for my horrible handwriting today. I equals I naught cosine squared theta. We're going to solve for theta in this case, so I need to get the i's together. I over I naught equals cosine squared theta. We're going to get rid of that square by taking the square root. So square root of I over I naught equals cosine of theta. And then I can just simply take the inverse sine, or cosine, sorry, of both sides. Theta equals the inverse cosine of the square root of I over I naught. Theta equals the inverse cosine of square root of the second intensity is 3 watts per meter squared over 5 watts per meter squared. And if we do that math, let's see, we have this over here. Let's clear everything out. 3 divided by 5. I'm going to square root that. I'm going to take the inverse cosine, and that's going to give me an angle of 39 degrees. The angle between those two should be 39 degrees. Whoops. Bother. Okay. So that is how Malice's law works. Now, I always like wearing polarizers. Many of you may have polarized sunglasses. And often fishermen may have polarized sunglasses. In fact, I'm going to put a picture of a fisherman I found on the internet. I don't know if his sunglasses are polarized or not, but you can see what a real fisherman looks like here. And you may ask, why do people wear polarized sunglasses? For driving or for fishing or things like that? And what turns out that there's sort of an interesting behavior that occurs with light, and really all waves, but especially with light, and it's called, it's a phenomenon that thankfully we don't have an equation for anymore. We used to have to calculate this. We don't have to anymore. But let's imagine here on the water, I'm going to make water blue, make it look like a nice pretty water for those beach vacations we're all going to take this summer. And we have some sunlight coming in. That sunlight is going to bounce off the water. Now, there's a little fishy down here. And obviously, if you're fishing, you want to kill the fish. So here's you in your boat. And with your gun. I'm not a big fisherman, so I don't really know how it works. You want to kill the fish. You want to see through the water to see the fish. Well, there's two kinds of light coming at you. Well, obviously the fish is going to have some light come up and it'll go to your eyes. Maybe you can see the fish. Notice refraction happening here. But there's also going to be some light bouncing off the water going to your eyes as glare. And that glare is not going to help. It's going to make things tougher to see in the water. You only see maybe the reflection of what's on top of the water, but you're not seeing anything underneath the water. But a funny thing happens. When unpolarized light hits a smooth, non-metallic surface, so water is a great example of this, the wet light becomes polarized in the plane of the surface. So for example, unpolarized light from the sun, it's just jiggling all over the place. After it hits the water, water is horizontal. The light becomes horizontally polarized. The horizontally polarized. As the horizontally polarized light goes to your eye, you want to block it out. So what are you going to put in front of you to block out that light? You're going to put a vertical polarizer. And what that vertical polarizer is going to do is it's going to block all of that glare. It's going to block all that horizontally polarized light. Now the light from the fish, well, it's not polarized. So it's only going to get knocked down by a factor of 2. And so now you can see inside to see that fish a little better. I have a good example here. I found this on the internet. I did not take this picture. It seems a little creepy, but it's a good example, like somebody's taking a picture inside somebody's room or something at their house, but whatever. So this is 2 images of the same setup, and I want you to focus on this window. Okay. This first window, we can't really see in that room very well. A lot of glare. We see the sun. The second one we can see much better. It looks like the window is open. Now it isn't. It's the same. It's the same image in both. The difference is there is a polarizer applied right here. Because this light coming off of this window, all that glare, that's polarized light. And if you can knock out that polarized light, you're going to be able to see through much better. Photographers do use polarizers to try to minimize reflections. Also makes the sky appear bluer. There's some neat things they can do with polarizers. Polarizers can be used in chemistry. Some substances, based on their concentration and a few things, can actually become polarized, or can actually polarize light. And so there are actually machines that chemists use that'll send polarized light through a substance and see how the polarization has changed after it goes through the substance. By looking at how the polarization has changed, they can figure out maybe what the concentration of the substance is or something like that. So polarization is a pretty neat topic. If you've ever seen a three-dimensional movie, in order to see a 3D movie, you need two different images to go to one image for each eye. The way they do this is with polarized glasses. You are wearing special types of polarized glasses that they shine two images on the big screen in front of you. The glasses only let one of the images in, and you see two different images. You see 3 dimensions. So this is polarization. Pretty neat little topic. I have a few videos following this, real short, like 5-minute videos, showing how polarization is used. One is going to show using microwaves, which makes polarization sort of easier to understand and see. The second is going to show polarization in terms of computer monitors, which is sort of interesting. And then the last video is a sort of fun one, looking at how you can actually make a filter for your screen where no one else can see what's on your screen except you with your special glasses. So check those out. The assignment for this week is a cognitive assignment, and I'm gonna have you do that, and I might put a worksheet up there. I'm not totally sure about that yet, but we'll have to see on that one. But it is a short week. Obviously, Friday is spring break, and Thursday is our special STEAM day. So hopefully we can have a little bit lighter week than we had last week. And do look forward to seeing y'all on our assigned day to talk about this stuff. So till then, this has been Mr. Reynolds. Thank y'all and have a good day.